Okay, so in this class, we will understand what exactly is differentiation. So differentiation is actually the slope of any graph. See, for instance, let us take the case of the displacement of a particle in 1D motion being given by the function displacement y as a function of time is, say, y is equal to 5 t to the power 5 plus 4 t to the power 3 plus 7. So I've just taken some complicated function so that even the slope is a function of time, and even the derivative of that velocity, which is again acceleration, is also some function of time. So if you apply the rules of differentiation from any table of differentiation, you will find that if you have y as a function of if you have y as a function of x as y is equal to a x power n, where a is a constant and n is a constant, then the rate of change of y with x, which is called as the derivative of y with respect to x, is going to be the constant a multiplied by the power n multiplied by x to the power n minus 1. So this is just one of the rules of differentiation for the function of the form a x power n. If you have a function of some other form, the result of the derivative will be some other form, some other function. So we just have to use those rules blindly and we can get along with our work in physics. So let me just demonstrate that the definition of dy by dx gives exactly this result for a function like this. So the same result you'll get from the basic definition of differentiation, which is that dy by dx is delta y by delta x in the limit when delta x tends to 0. So here what I mean by x is whatever is plotted on the x-axis. So in physics problems, usually on x-axis we have time and on y-axis we have displacement. So if you have some complicated function, it could be when t is 0, it goes to 7, right? So let us say this is the 7 value, and then it will turn, since this degree is 5, it will turn 5 times, I suppose. So something like this. Okay, so it's some complicated function. So if displacement is like this, the velocity is the slope of this function at that point. If we take some time here, for instance, the slope at this instant is the tangent at that point. And the velocity at this point, if you want to find, it will be the tangent at this point. If you want to find the velocity at this point, it will be the tangent at this point. Velocity at this point will be the tangent at this point. So as you can see, the slope is changing with time, which means the object is speeding up, slowing down, speeding up, slowing down with time. At each instant in time, it has a different speed or velocity. So when you differentiate this function at a particular value of time, you obtain the slope at that time. So differentiation gives the instantaneous slope. Instantaneous slope of a graph. So it gives instantaneous slope, that is the slope of this tangent. Okay. So how will you obtain that? By solving this ratio. So if you have, let us take a function of this shape. So if you want to find the slope at this time, let us say this is t equal to 1 second, this is y and this is t. So if you want to find the instantaneous slope at this time, you are actually looking for this slope of this tangent. Okay. So now if you start with t equal to 1 second to t equal to 2 seconds. So in this case, the delta t or change in time is 1 second. Then what you do, you take 1/10 of that, say till here. Then the time interval would be, delta t would be 0.1 second. So in that case, so in the first case, your delta t was 1 second, right? So the slope would be the slope of this 1 second duration would be delta y by delta t you would get this slope of this line. Basically, you would get a slope of this secant. Okay. Now, as you shrink this delta t to this much value, then delta y would be this much, and the slope would be this. So as you can see, the slope of the secant almost coincides with the original slope, which was this red line. So the original slope of the tangent at t equal to 1 second almost coincides with the tangent, almost coincides with the secant when delta t approaches 0. So if we take the ratio of this delta y by delta t, as delta t approaches 0, the slope of the secant would become equal to the slope of the tangent. So slope of secant delta y by delta t approaches the value of slope of tangent at t equal to 1 second. This one is the example we want. We want to find the slope at t equal to 1 second, so I'm saying that. If you want to find the slope at t equal to some other value, you can again find delta y by delta t starting from that time value and start shrinking the value of this delta t. Then delta y by delta t will approach the instantaneous slope at that value of t. So in our example, we have limit delta t tends to 0, delta y by delta t. So now if you want to calculate this, what we will do is delta y we know is the value of y at the bigger value of t, which is t plus delta t. So this t is actually t plus delta t. This is t plus delta t is this value. So y of t plus delta t minus y of t. That will give you delta y. And delta t you know already. So your velocity is delta y by delta t, which means it is going to be y of t plus delta t minus y of t by delta t. So as delta t gets smaller and smaller, this ratio you will calculate, and you'll find that this ratio will approach the theoretical value, which is this. Okay, so for example, let's calculate the theoretical value first. So we are taking the function as y is equal to 5 t to the power 5 plus 4 t cube plus 7. So dy by dt is equal to 5 into 5 into t to the power 4 plus 4 into 3 into t square plus derivative of 7 is 0, which gives 25 t to the power 4 plus 12 t square. Okay, so if you want to find t at 1 second, velocity at t equal to 1 second, so velocity of t equal to 1 second would be 25 into 1 power 4 plus 12 into 1 square, which is 25 plus 12, which is 37 meter per second. Okay, so this is the answer of velocity at t equal to 1 second if you just apply differentiation formula to the function of displacement y as a function of time, right? Now let us say prove that we will get the same thing by the definition of differentiation, which is that velocity is going to be delta y by delta t. We are going to prove that velocity is delta y by delta t when delta t tends to 0. Limit delta t tends to 0. So let's do that using Excel. So here I have typed, so this is the equation y, this is the equation v, this is the equation acceleration a, but we are not going to acceleration now. You can do it as extension for yourself to practice. So let's say you want to find the velocity t equal to 1 second. If we use the ready-made differentiation formula, we get 1 second the velocity is 37 meter per second. This is just 25 plus 12 because t is 1. So 25 into 1 power 4 plus 12 into 1 squared is 25 plus 12, which is 37. Now to check whether the same result we get by the differentiation definition of delta y by delta t, where delta t tends to 0, let's do the calculation as follows. So we are taking t to be 1 second. So the displacement at t equal to 1 second is obtained by substituting the function for y, which is 5 into t to the power 5 plus 4 into t to the power 3 plus 7. So I just keyed in the equation of y. And delta t is the time interval we are going to use. We are starting with a delta t of 1 second, then 0.1 by order of 10. A factor of 10, we are decreasing the time interval from 1 to 0.20 followed by 1. So if delta t is this, the time after that delta t will be t plus delta t, which is calculated here. So I've used this dollar symbol so that my formula doesn't change the C10 address, because C10 is the address which gives me the value of time. So, sorry, C10. Yeah, value of time, which is 1 second. So this is C10. So t plus delta t is supposed to do this value 1 plus delta t. So 1 plus 1 is 2, 1 plus 0.1 is 1.1, 1 plus 0.01 is 1.0, and so on. Then I want to find the new displacement. Old displacement was 16 at t equal to 1 second. So the new displacement after t plus delta t second is obtained here. The same formula I'm using, but now I'm using the time value as t plus delta t. So F11, in the next cell it will be F12, next cell it will be F13, then F14, F15, F16, and so on. So I'm finding a new displacement. Then delta y will give me the difference in displacement. So I'm doing this final displacement minus initial displacement of 1 second at 1 second. So this, for this initial displacement, I'm using the dollar sign so that I can keep using the same address for the remaining cells. So everywhere it will be C11, 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 C11. So final displacement minus C11. Then finally, to find the velocity at 1 second using delta y by delta t, I'm just dividing this delta y by the corresponding delta t. So for example, here H11 by E11. This is E, this is 11, so this is E11. Then H12 by E12, H13 by E13, and so on. And as you can see, as delta t approaches 0, the ratio of delta y by delta t approaches 37. So it improves by one order of magnitude, by power of 10 every time, a multiple of 10 every time. So if this approaches 0 point, if delta t approaches 10 power minus 30, this will also be 37, followed by some 30 zeros and then some 1 or 2 or whatever. And the accuracy will increase proportionately to how small my delta t becomes. So the theoretical value is the actual true value, which is 37. It's the analytical solution. And what we obtain here is called the numerical solution. By approximating delta t to 0, we obtain as close to the analytical or theoretical solution as possible. Hope now you understand what is differentiation.